Hello friends, in this video we are going to study about what is stability and the types of stability in a control system. So let's start with our topic. First we will start with what is stability. So stability, it is one of the most important property of a system, and it refers to the ability of the system to perform satisfactorily. So that we can say that stability, it is a measure of the performance of the system. That is how good the performance of the system is, whether it is stable or it is unstable. Okay. So how we define stability? So a stable system is one in which small input lead to an output that do not diverge. So to understand this definition of a stable system, let us first take an example of a pendulum, and then with respect to the pendulum, we are going to see that what type of system will be called a stable system and what will be called an unstable system. Just remember this line that a stable system will have in which the small input, it is going to produce an output that do not diverge. So let's take an example of the pendulum. So we have a pendulum which is hanged from a rigid surface. Okay, this dashed line, it is showing a rigid surface, and through this rigid surface this pendulum has been hanged. Earlier the pendulum was in the vertical position, that is 90-degree to it, and this was the initial state of the pendulum. Now when a small input force, that is Ft, is applied on the pendulum is shifted from its initial state. Okay, so this input, it is producing the output xt, which is the angular displacement of the pendulum. So xt is the angular displacement, and Ft, it is the input force. Okay, so this input force Ft, it is producing the output xt, which is the angular displacement, and we can see that a small input, it is producing a small output. This output, it is not increasing. Now if we release this pendulum from this position, then due to the gravitational force, this pendulum, it is going to do the to and fro motion, that is it will go to this side, again it will come to this side. So in this way it is going to uh, perform the to and fro motion around this initial state. Okay, due to the gravitational force and due to the frictional losses, this pendulum will come to finally this initial state or the rest state. Okay, because due to the forces, the frictional losses and the gravitational force, this distance it is going to decrease, and finally the pendulum it is going to come at its initial state. Okay, so at last it will come to slow down and it will come in its initial state. So this is the case of a pendulum which is hanged from a rigid surface, and in this case the input applied it is producing a small output, which is the angular displacement of the pendulum from its initial position. Okay, so this system, this type of system will be called a stable system. Because we have studied in the definition of stable system that it is the system in which the small input it leads to that output that do not diverge. Do not diverge means with respect to time that output is not increasing. Okay, with respect to time it is decreasing to it. So the angular displacement with as the time passes it is becoming less. So small input is producing small output, or bounded input is producing a bounded output, so it will be a stable system. So this was the case of the pendulum. Now if we take the case of an inverted pendulum, so inverted pendulum will be like this. This will be the rigid surface. It is the initial state when it is at 90 degree, and this is the pendulum. So in this case of the inverted pendulum, the pendulum was at in the initial state it was at 90 degree from this surface. Now when we release this pendulum, this deflection from the initial state will be large, that is this xt will be large, because on this pendulum this force applied by the gravity will be more. Okay, so this force will try to bring this pendulum to fall at this surface. Okay, so in this case the deflection produced in the system is large. So small input it is producing a large output, and the output we can say that with respect to time it is diverging. So small input produces an output which diverges with time. Diverges, or we can say increases with time. So this inverted pendulum case, it will be the case of an unstable system. So we have defined the stability, and then we have defined that what is an unstable system and what is a stable system. That stability, it is defining that how good the performance of the system is. Okay, and stable system is one in which the small input it is producing an output which is not diverging with time, and in an unstable system small input will produce an output which diverges with time. So now we can define the stability with respect to an LTI system. LTI system means a linear time invariant system. So how the stability is defined for a linear time invariant system? Let's see. So for a linear time invariant system, a system will be called stable if the following two conditions are satisfied. So the first condition for the system stability is the BIBO stability concept. This is called BIBO, that is bounded input, bounded output stability concept. So this concept says that when the system is excited by a bounded input, the output should also be bounded. Okay, bounded input means that we have a limits for the input. Okay, and this input is just like not ranging from infinity or like such value of the input. So bounded input means a defined input is there, a small input or a value which is defined for the input, and that input is producing the output which is also bounded. Okay, it doesn't means that we have applied the input and the output it is increasing with time. The system is producing an output whose value is increasing with time, so that will be an unbounded output, and it is at the end of the time it is reaching towards infinity. So such type of system will be unstable. A stable system will have, if it is excited by a bounded input, then it is going to produce a bounded output. So this is the BIBO stability concept. Now the second condition is that in the absence of the input, the output tends to be zero. That means if no input is applied to the system, then the output of the system should also be zero, irrespective of the initial conditions of the system. Means if there are some initial conditions due to which the output is produced and no input has been applied to the system, so that condition you don't have, those initial conditions you have to not consider. So irrespective of the initial conditions, if there is no input is not applied to the system, then the system should also produce no output. Okay, so these are the two conditions which should be satisfied for a linear time invariant system to be stable. Okay, now we are going to define the stability with respect to a control system, because our subject is control system. So we have to see that when will be a control system called a stable system and when it is called an unstable control system. So for control systems, the stability it is defined in respect to the location of the roots of the characteristic equation in the S-plane. So here we will study that what is the location of the S-planes, like whether it is in left half or right half of the S-plane, and according to the location of S-plane, how the stability has been defined. Okay. So a control system will be said to be a stable system if all the roots of the characteristic equation that lies in the left half of the S-plane. Okay, so S-plane means we have imaginary axis and the real axis. This is our imaginary axis. This is real axis. This is positive and this is negative real axis. This is positive imaginary and this is negative imaginary axis. So this is S-plane. Now it is saying that the roots should lie on the left half of the S-plane. That means on this side. This is left half and this is right half. So all the roots of the characteristic equation for a stable system, they should lie on the left half of the S-plane. Okay, so that system will be a stable system. Okay, now an unstable system will be that in which even one of the roots lies in the left half of the S-plane. Suppose the system is having 4 roots, and out of the 4 roots, 3 roots are lying on the left half and 1 root is lying on the right half of the S-plane. So that system will be an unstable system. So the system which is having all the roots on the left half will be a stable system, and if even one of the root is lying on the right half of the S-plane, then that system will be an unstable system. So the root will lie on the left half of the S-plane if it has the negative real part. Means a root of the characteristic equation, if it is a real number, okay, then that real part should be a negative real part. Okay, this video is in continuation of the topic what is stability and type of stability in a control system. So a stable system will have a negative real part and unstable system will have a positive real part. Okay, because the roots, it can be a complex number, it can also have only the real part and only the imaginary part. Okay, so that real part, if it is negative real part, then that root will lie on the left half of the S-plane. So we can also say that if the roots of the characteristic equation, they are having negative real part, then that system is stable, and if the root is having a positive real part, then it will lie on the right half of the S-plane, so the system will be unstable. So this is how the stability is defined on the basis of location of the roots on the left half and the right half of the S-plane. Now if the root, it lies on the imaginary axis, then how the stability is defined, let's see. So a system is called marginally stable or limitedly stable if the roots of the characteristic equation, they have 0 real part and pole is not repeated. Okay, that is the characteristic equation, the root of the characteristic equation, it is having 0 real part, only imaginary part is there, so it will lie on the imaginary axis, and it is not repeated, that is we are having non-repeated roots on the imaginary axis, so that system will be called marginally or limitedly stable. Now the second case is that if the roots are on the j omega axis, that is the imaginary axis, and simple. Okay, that is we are having the imaginary roots on the j omega axis, then also the system is marginally or limitedly stable. If all the roots are lying on the left half of the S-plane and except one pair of root which is lying on the imaginary axis, then also the system is marginally stable. So the system is called marginally or limitedly stable if it has non-repeated roots on the imaginary axis, that is 0 real part is there, only imaginary part is present. Also if the roots are, that is imaginary roots are there and the roots are simple, then also it is called a marginally stable. Now all the roots are lying on left half, only one is lying on the imaginary axis, then also it will be called a marginally or limitedly stable. So this is how the location of roots, it is defining the stability of the system. Let's see the table for it. So we have these four conditions: all roots having negative real part, at least one root has positive real part, repeated roots on j omega axis or at origin, and non-repeated roots on j omega axis or at origin. So for this, the system will be called stable system. So how we are going to define all roots which are having negative real part? So on the S plane, if we draw, the roots which are lying on the left half means this is imaginary axis and this is real axis. Now at least one root has positive real part. It means the roots are lying on the right half of the S plane, that is on this side. Now repeated roots on j omega axis or at origin, it means if we have this as the S plane, this is our imaginary axis. So roots are lying on this imaginary axis, but the roots are repeated roots. So they can be on imaginary axis and on origin, or it can be on the imaginary axis. So this will be the case of an unstable system. Now non-repeated roots on j omega axis or at origin means if we have this as the S plane, the roots are lying on the imaginary axis. So this is the case of marginally or limitedly stable. So this is how the location of roots, it is defining the stability of system in the control systems. Now there are two things also, the damping ratio and the impulse response. They also define the stability. Let's see how. So a system is said to be stable if the damping ratio is positive, and if the damping ratio is negative, then the system is unstable. Okay, positive means the value of del should come out to be greater than 0. So if damping ratio is positive, the system will be stable. Negative damping ratio means del is less than 0, so the system is unstable. Okay, now in case of impulse response, if the impulse response is approaching 0 as the time approaches infinity, then the system is said to be stable. Okay, so as the time is increasing, that is time is approaching towards infinity, the impulse response of the system should approaches 0. So that system will be called a stable system. So we have defined the stability of a control system with respect to location of roots in the S-plane, and second, according to the damping ratio, that whether it is positive or negative, and also according to the impulse response value, that as the time approaches infinity, the impulse response should approach towards 0. So this is how the stability is defined for the control systems. Now let us see that what are the types of stability in the control systems. So in control systems, we have two types of stability. One is absolute stability and the other one is relative stability. Okay, so we have absolute and relative stability. Absolute stability, it is the stability of the system with respect to the parameters of the system. Like if the system is stable for all the values of the parameters, then the system will be called absolutely stable. That means if we are changing the values of the parameters of the system, then for all the values of these parameters, the system is coming out to be stable. So for all values it is stable. So we can say that overall the system is absolutely stable. Okay. So this absolute stability, it is defined with respect to the parameters of the system. Now relative stability, it refers to the stability of the system, that how much the system is stable. That means it is a comparative measure of the stability, that how much the system is stable it is, whether it is less stable, whether it is more stable. So when we are making the comparison of stability, then we define relative stability. So let's have the definitions of absolute and relative stability. So these are the definitions of absolute and relative stability. Now, how we measure absolute and relative stability? As absolute stability, it is the stability with respect to variation in the system parameters. So it can be determined from the location of the roots of the characteristic equation in the S-plane. And the relative stability, it is defined by the parameters or specifications of the system like maximum overshoot and damping ratio, gain margin, phase margin. So these specifications define the relative stability. So these are the measures that how we can measure absolute and relative stability. Now, as we have said that absolute stability, it is defining the quality of stability of the system. That is how much, the quality of stability, like with respect to variation in the parameters. Like if we are changing the values of parameters, the system is it stable or unstable? So absolute stability, it is the qualitative analysis of stability, whereas relative stability, it is the comparative analysis of stability. That means we are making the comparison that which system is more stable. Okay, so we can say that it is a comparative analysis. So these are, we can say that these are the differences between the absolute and the relative stability. Now, this relative stability, we define it with respect to the settling time of the system. So a system is said to be relatively more stable or unstable on the basis of settling time, because the location of the roots are, like if the roots are locating nearer to the imaginary axis, then the system will have more settling time. Okay, so if we take an example here, we are having two roots. This is alpha 1 and this is alpha 2. So we can say that this, both these system are stable system because the roots are lying on the left half of the S plane. But which system is more stable, first system or second system? How we can define? On the basis of the settling time. The system which is having the root which is nearer to the imaginary axis, it will have more settling time. Okay, so this is having more settling time in respect to this second system. Okay, so this system will be a stable system and this will have less settling time. The second system will also be a stable system, but it will be relatively more stable than the first system because it is having less settling time. Okay, so this is how the relative stability can be defined by using the settling time. Okay, so in this video, we studied about what is stability, how the stability is defined for a linear time invariant system. Then we studied that how the location of roots in the of the characteristic equation in the S plane, they define the stability of control system. And in the last, we studied the types of stability in a control system, absolute stability and relative stability. So I hope that this video is clear to you. Thank you.